The t-distribution, just like the standard normal curve, is bell-shaped and unimodal. It is symmetric about t is equal to 0. However, its variance is greater than 1. This makes it wider and flatter in the middle. It has more area in its tails than that of the standard normal curve. Its shape depends on the sample size, or n. As the sample size n becomes larger, the t-distribution gets closer to the standard normal distribution. So here's an example of standard normal distribution and a t-distribution. Statistical analysis on some studies which cannot be done using the normal distribution can be done using the t-distribution. The t-distribution is used with small samples taken from population that is approximately normal. The z-statistics in the previous lesson uses the value of population variance, while the t-statistic below uses the sample of deviation, especially when the population variance is unknown. The z-statistics is used when n is greater than 30, while the t-statistics is used when n is less than 30. So this is the t-distribution formula, where t stands for the student's t-distribution, x bar stands for the sample mean, the sign mu stands for population mean, s for sample standard deviation, and n for sample size. To find a value in the table of t-critical values, here is to adjust the sample size by converting it to degrees of freedom. The number of degrees of freedom is equal to the number of the remaining values in a dataset that are free to vary after one or more values have been deducted. In the use of the t-distribution, one value is deducted. So this is the formula for the degrees of freedom, where df is the degree of freedom and n stands for the sample size. A student researcher wants to determine whether the mean score in mathematics of the 25 students in grade 8 section Newton is significantly different from the school mean of 89. The mean and the standard deviation of the scores of the student in section Newton are 5 and 15, respectively. Assume a 95% confidence level. Take note of this problem and let's move on to step number 1. Let's take note about the formula of the degrees of freedom. In this problem, our sample mean, or the n, is 25. So let us try to consider that and apply it to the formula. So the degree in freedom is equivalent to n minus 1. As I've said, 25 is the sample mean here, so degree of freedom is equivalent to 25 minus 1. We all know that 25 minus 1 is 24, so therefore the degree of freedom here is 24. Now to find the critical values, we need to use the table of t-critical values referred to the appendix. So the confidence level is 95%. And this is our solution. So using the t-critical values table, look at 24 under the column headed df. Move to the right along the row until reaching the column headed 0.05, area in 2 tails, or 0.025 for area in 1 tail. So for the solution, the critical value here is 2.064. Compute the test statistic t. T is equals to x bar minus mu divided by s and divided by square root of n. So it is 95 minus 89 divided by 15 divided by the square root of 25. And the answer for that is 2. The compounded value of t is equal to 2, which is smaller than the tabular value of 2.064. Therefore, the value of the test statistic or compound t-values does not fall in the critical region. Therefore, the mean score of grade 8 section Newton in mathematics is the same with mean score of all the students taking up grade 8 mathematics. A sample size n equals 20 is a simple random sample selected from a normally distributed population. Find the value of t such that the shaded area to the left of t is 0.5. Find the degrees of function or df. So our formula df is equals to n minus 1. So that would be 20 minus 1 and 20 minus 1 is 19. Since the t distribution is symmetric about 0, then the area to the right of t is 0.5 and to the left is also 0.5. In the table of t critical values, move down the first column headed to the df 19, then move to the right along this row reaching the column headed 0.05 in area in one tail or 0.10 area in two tails.